So let's start from quantum theory of angular momentum, quantum mechanical angular momentum. Quantum theory of angular momentum. I'm going to remind you what is angular momentum, and I'll try to build a theory of angular momentum in quantum mechanics. And I have to apologize from the very beginning. There are many calculations which I'm going to skip. I don't just want to waste time, I want to give you an overview. But each calculation is not that bad. I mean, you can do this yourself. So we will see. So when you talk about angular momentum, let me use the label L for angular momentum. The definition is the following. It's a cross product R cross P. So R is the position of particle. Let's say you have a coordinate system, X, Y, and Z. And then you have particle, so you have a vector which defines the position of this particle. The particle may have some mass m and some velocity v. So you can construct a linear momentum and you take a cross product between r and p, and this is a definition of an angular momentum. So some of you who took physics 1, they know a little bit about angular momentum. So when you move to quantum mechanics, instead of angular momentum, you will have an operator of angular momentum. And 1 hour, I'm going to talk about this operator. So this operator can be constructed as cross product of two operators, R and P. We have some experience of working with R and P. So now we have to build a cross product between these two vectors. So basically you have three operators, X component, Y component, and Z component. Okay, so let's start to work with this slowly. So for example, vector R, I can present it as a combination of three components, X component, Y component, and Z component, or simply X, Y, and Z. So if you're talking about operators, then there should be just X hat, Y hat, and Z hat. Yeah. What about vector P, the linear momentum? The same. I have components Px, Py, and Pz. So I can write it as minus I h bar d over dx. And let me just finish it. Minus I h bar d over dy, and the same for the z component. Yeah. And maybe I can write it here. So you see, not only X component of the linear momentum, I also have other components. And this is very important because it's a 3D problem right now. It's not 1D. So in 1D, we just had X and Px, and that's it. Now I have two more components which represent me the angular momentum and 3D motion of my particle around some center, let's say. Now, we have to move further. We have to make one more step. We have to build the cross product between R and P. And there would be operators for X, Y, and Z component of my angular momentum. This is something you may not know, Something I probably have to remind you or just maybe explain. The x component of angular momentum would be y multiplied by pz minus z multiplied by py. Have you seen this before?
No,
No.
I think no. Yeah.
So this is a cross product in components. So the y component, I would say zpx minus xpz, and z component, let me think about it, it's going to be xpy minus ypx. There are rules, but this is how you find a cross product between R and P in components. So then I would try to move to operators. What would be the operator of Lx? I have to replace each of them with the corresponding operator. So I'm going to put minus I h bar as a common multiplier, and then y z component of angular momentum is d over dz. Sometimes people just use shortcut like this. It's just a shorter notation for the partial derivatives. So I have y minus d over dz, and then minus I h bar goes in front. Then I have to subtract the second part. The second part would be what? Z, yeah, and partial derivatives over y. Can you help me with Ly? What kind of operator is this? Z, yeah, multiplied by what? So you replace px with the corresponding operator. Yeah? Your px is d over dx. Minus what?
XD.
xd over dz. Very good. And the last one?
XDY minus y dx.
Perfect. Very good. So then I'll try to remember that, okay, I use this eigenvalues and eigenstates for operators to find such states in which value of these operators are certain. I can try to calculate commutators between these operators. I know some techniques which involves rising and lowering operators. Basically, I can build the entire algebra just based on the operators. And to some extent, I'm gonna do this. I'm gonna just sketch probably the solution, not really prove it to you. But I'm gonna show you like a way which you can follow. But this would, for me, this would be the starting point. This is called angular momentum operator in coordinate representation. When your coordinates are just normal multiplication, and momentum is just the partial derivatives over the corresponding variable. Spherical coordinates. I'm going to switch to spherical coordinates after a while. So the spherical coordinates are the following. if you have a x, y, and z, and if you have a point here, of course you can try to describe it with x component, y component, and z component. I don't know if this picture makes sense or not. So you have a z component, x component, and y component of this vector. But there is another choice. So you can introduce the distance from the point to the center, r. You can introduce angle theta. There's going to be angle between vector r and the positive z direction. So you can say my z equals r cos theta after this. So you see, cos theta multiplied by r should give you the z component. You can introduce this angle phi, which is angle in the xy plane, which will give you the orientation of this plane, which is vertical right now, to xy plane. So the orientation of this plane relative to the x direction. So then the length of this part inside the xy plane would be r sine theta. So r sine theta is this one. And if I multiply it now by cos phi, I'm going to get my x component. And finally, y component would be r sine theta and sine phi. So these are y component and x component. What I just wrote you as the transformation from spherical 3D spherical coordinates to Cartesian x, y, and z components. What I would like to do now is do something opposite. I would like to change coordinates here from Cartesian x, y, and z to spherical. And I'm going to skip this step. I'm going to just write the answer. And I'm going to write answer only for LZ, because LZ looks very simple. Lx and Ly, they look a little bit more complicated in this coordinate spherical, and I will explain why they look more complicated. So then going to be without proof. If I try to go from x, y, and z to r, theta, and phi, then my LZ would be minus I h bar d over d phi. How do you like it? It's very nice because it's very simple. The meaning of this actually even more nicer. What does it mean d over d phi? D over d phi means that you take a function at some angle and you try to change this angle by delta phi, and this delta phi goes to 0. Yeah. What does it mean, phi plus delta phi? It's a little bit of rotation, yeah? When you try to change the angle, so you have an angle phi, and you try to rotate your system about z-axis. So I would just say proportional, but this is not real proportionality. It's more like conceptual. It's about rotation. Rotation about what axis? About z-axis. So the operator LZ can be represented or can be related, it's a better word, to rotation about z-axis. When you try to vary your function, in terms of angle phi and see what will be the difference. This is what represents the derivatives over angle phi. What can you, okay, let me draw this again for you. If this is x, y, and z, then when you start to rotate around z axis, this is your operator Lz. Or operator Lz is related to rotation about z axis. What about Lx operator? Well, Lx or Lx would be rotation about x-axis. X-axis. I'm not going to write the expression for Lx because simply I don't have angle in zy plane like angle phi. So this rotation looks a little bit more complicated than just d over d phi. And for the same reason, the operator Ly, you can definitely get this. Just do the transformation. Simply the expression is not going to be simple. Rotation about y-axis. But Lz looks very simple because my angle phi was defined to represent the direction along z direction. That's why it's so simple. If you would like, you can just do the exercise. You have these expressions and you just substitute z and y into these expressions and you simply just calculate it. Just do the transformation. Apparently I can spend 20 minutes on this transformation during this class, but at home this would be a very nice exercise for you. So just plug it in and see what you're gonna get for Lx and y and Lz. For me, this would be just enough if I focus on Lz for now, and if I understand the meaning of Lx and Ly. Yeah? Ly, Lx. Okay, let me put some like period at this point and summarize. What is angular momentum? It's a cross product of r cross p, the normal definition like we would use in classical physics. When you move to quantum mechanics, each quantity becomes an operator. And you just put instead of r, operator r, and instead of momentum, you put the corresponding operators. Then I'm going to switch coordinates to spherical. And this is a definition of the spherical coordinates. And then I can calculate my operators in spherical coordinates. And I did it without proving it to you. Basically, I just wrote the answer for you. This would be one big achievement for me. The second part, what I will need, is a commutation relationship. If I try to calculate commutators, so for example, if I would like to calculate commutator Lx with Ly, the meaning of this commutator would be Lx Ly minus Ly Lx. It has a beautiful geometrical interpretation because first Lx, you do rotation around x-axis, and after you rotate around x-axis, you rotate your vector around y-axis. And the first pair, you do the opposite order. First you rotate around y-axis and then around x-axis. And then you compare the difference. What will be the difference? And you can calculate it. Just plug this Lx and Ly and calculate commutators. We know properties of how we calculate commutators. Apparently, I'm gonna get h bar square and some mixture of this vector r and some partial derivatives all around. So if you do your calculations carefully, you're gonna get something like this. I h bar lz as an operator. So meaning that it's gonna be h bar square x dy minus y dx, if I'm not mistaken, yeah? LZ is minus h bar, yep. Again, I'm not proving this to you, I'm just telling that this commutator would equal LZ. Then if you do this rotation in this order and compare them, the difference would be equivalent to rotation along z direction. So the rotations in 3D space, the order between these rotations is important. You can just interchange rotations. Lx and Ly, they know about the order, in which order you rotate the vector. Okay, but from all this line, I need only the answer. That commutation between Lx and Ly would be just I h bar Lz. If you don't believe me, check it at home. It would be relatively easy for you. Just calculate the commutators. Now, I can do some shifts in this relationship, so I can get Ly Lz. Simply, instead of x and y, I can do y and z. If you do commutation relation between Ly and Lz, you should get x. And z and x, you should get y. So there is certain symmetry. So if I shift it, y to the left, z to the left, and x, then I'm get something like this. And if I shift it one more time, I'm gonna get Lz and x, yeah. These are canonical commutation relationship between angular momenta components. There is a shorter way to write it down, but I will just keep it in this form. This is the basis of the corresponding algebra. Remember, the commutation relationship were very important for me. So we can compare this for linear momentum and vector r. So if you have a px, any component of px or momentum, any component, pi and pj, they commute. It's a different from angular momentum. That means it doesn't matter in what order you apply linear momentum. Ri, rj, they commute for any I and j. The only what don't commute is p and r. But they should be of the same component. So if I put I and j, the I and j should be the same. In this case, I'm going to get minus I h bar, and this is called delta symbol. So the delta symbol is equal to 1 if they're identical, or 0 if they're different. It's called Kronecker delta. So I just want you to compare. So the commutation relation for linear momentum and then linear momentum and coordinates They're very different from commutation relationship for angular momentum. And I'm going to build a little bit of algebra of this angular momentum. And I will need this commutation relationship, which you can prove, basically. And the starting point for proving could be just this one, because you know how to calculate commutation relationship for this operator P and R. Okay? So far, so good. So now I would like to find eigenvalues and eigenvectors of these operators and build what's called quantum theory of angular momentum. So then you have to bear with me a little bit more, because I will have to introduce a couple more operators. L plus, which is going to be Lx plus Ly. I'm going to call this rising operator, and L minus, which is going to be Lx minus I Ly. Compare this operator to this operator is compared for operator A, which was proportional to x plus IP, or a dagger. Kind of a linear combination, remember, for simple harmonic motion of operator x and p. Here I'm going to build a linear combination between x and y components. So why this L plus, L minus are so important for me? Well, because if you take Lz and you calculate commutation relation with L plus, you can get something like L plus again. And the coefficient would be just h bar. If you take Lz and you calculate commutator between Lz and L minus, you're going to get minus h L minus. Remember, when we have this h for simple harmonic motion, commutator with a dagger, we got h bar omega a dagger, and commutation operator h with a, it was minus h bar omega a. What did we say about these operators last time? Operator a dagger is going to rise energy by h bar omega. And I could prove it to you, and if you look at that line from the previous lecture, you could see how we can prove it. What was the meaning of operator A? Operator A can take this energy and it will lower down this energy by h bar omega. Now, look at this commutation relationship. What can you say about operator L plus? What can it do, this operator? It's going to be a rising operator or lowering operator, if you compare.
It will rise.
It will rise. What quantity is going to rise?
Quantity?
Yeah, because in simple harmonic motion, operator A dagger was rising energy.
Yeah.
L plus will rise what?
The momentum.
Not even momentum, the z component of the momentum.
Yeah, exactly. The z component
will rise Lz. By how much? Before it was this value.
H.
Now
H bar.
by h bar. What about L minus? What can you say about L minus?
It will lower.
You lower LZ by
H bar.
H bar. If you want, I can prove it to you, because I can prove at least one of these lines. I didn't prove anything up to now. Maybe if you want, I can show you one of these commutators just as an exercise. Yeah. So example or exercise. So I'm gonna take LZ commutator with L plus. Wait a second. My goal was to say Z and plus. So then it's gonna be LZ, and L plus was defined as Lx plus I Ly. So I can split it into two commutators because I know that they are linear. So I'm gonna have LZ Lx plus Y LZ Ly. Z and X is a commutator. Let's go back and let's look at this one. Z and X. Actually, I know this commutator, yes? It's going to be I H bar Ly. I H bar Ly. This one. What about the second one? I multiplied Z and Y. Z and Y. Y and Z is Lx. If I have Z and Y, I need just to change the sign, yeah? So then it's going to be minus I H bar. And Lx. Do you agree? Then I'm gonna put H bar outside, and I'm gonna have I Ly, and here I'm gonna have my I and minus I is 1, just plus Lx. But what is this? This is my L plus, yes? Did I prove it to you? There's a commutation between LZ and L plus, you're gonna get the same L plus with coefficient H bar. So the second one you can check at home by yourself. Just repeat the calculation, put negative sign here, and you will see that you're gonna get negative H bar L minus. Okay, that was another important step for me if I would like to build the theory of angular momentum in quantum mechanics. And again, don't take it it's not a complete description. I'm trying to just give you the hints how it should be. One more step before I start working with the angular momentum and eigenvalues and eigenstates. There is an important operator which called L square. This is like a magnitude of the angular momentum square, L square. So the L square by definition is my Lx square plus Ly square plus Lz square. So if you want, you can just take these definitions here and just make it square and plug it into this L square. But the meaning of this L square, it's the magnitude of the angular momentum square. It's not component anymore, yes? Magnitude of L squared. So this operator has some properties. For example, one of the important properties that if you calculate commutator with L square with any component, let's say x component of angular momentum, you're gonna get 0. And so on. How can we understand this statement? Remember what I told you about LZ. LZ operator can be related to rotation around z-axis. L square is the magnitude of the vector. Does magnitude change if you rotate coordinate system? It does not change, yes? The magnitude of this vector is not going to change if you rotate it about y direction, about z direction, or about x direction. The meaning of this commutator would be applying operator of rotation around the corresponding axis. And this is the magnitude of the vector, it's the length, yes? And length does not change if you rotate it about any axis. So we don't need it, but if I take p square and try to rotate it around z direction, I'm going to calculate this commutator. My answer would be 0. And it's not only about z direction, it's about any direction. What can you tell me about if I take vector r and make it square, and you calculate commutation with Li? What you gonna get? The same, 0. So there is no wonder that this operator will commute with each of the vectors. And the meaning of this operator, it represents me the magnitude of angular momentum. The only difference is that it's magnitude squared. It's not just a magnitude. It's not L absolute value. It's magnitude squared. So, and this is very nice operator, and also we can say that L square will commute with L plus, and of course L square will commute with L minus, because they are linear combination of x and y. So L plus and L minus also commute. This is important for me. Finally, why I so worry about commute operators or they don't. If two operators commute, I can pick Eigen functions of these operators simultaneously. So for example, let's say my commutator L square and LZ is 0. So basically this means that L square LZ is the same as LZ and L square. I can just interchange them without any problem. And let's say I have an operator, a function, which is Eigen function of operator L square. my question, okay, will it be Eigen function of operator LZ because I commute? I can try. I can apply operator LZ to this. So let's say I'm going to build a new vector LZ, apply it to y, and I'm going to apply operator L square to this vector. What's going to happen? Because I can interchange them, yes, they commute. I can put it like this. LZ multiplied by what? L square and y. Does it make sense? I want to interchange them. So I just change the order because they commute. But operator L square multiplied by y, if it's Eigen function, I can replace the action with some eigenvalue. I can say lambda LZ multiplied by y. So what is the conclusion? If my vector y is eigenfunction, what can you say about LZ and y? I apply it to y. Y and LZ multiplied by y, they both eigenfunctions. But not just eigenfunctions, they correspond to the same lambda. Can you see this? Y is eigenfunction. When I apply L square, you get the same function multiplied by lambda. LZ applied to y, it's a new vector. But if I apply L square, because I can change the order, I can get the same LZY with the same lambda. Does it mean that the both of them, y and LZY, they're the same eigenfunction, which corresponds to the same eigenvalue? So under some assumption, I can conclude that when you apply LZ to y, it is the same eigenfunction as y. Maybe some constants here. Because operator LZ may change this function by, let's say, a phase or a constant. That means that y is eigenfunction of LZ. So the conclusion, if you know that two operators commute, then you can pick eigenfunction, so they will be eigenfunction of two operators at the same time. So they share eigenfunctions. In quantum mechanics, it's very important. If you have the same function and this function corresponds to its eigenfunction of LZ and L square, that means it has certain value of LZ, and at the same time, it has certain value of L square. So that's why these commutation relations are very important for me. I can pick my functions. They are at the same time eigenfunctions of L square and LZ, for example, or maybe L square and Lx. But can I have eigenfunctions which are the same which are eigenfunctions of Lx and Ly at the same time? No, because they don't commute. Can I have eigenfunctions which are at the same time eigenfunction of Ly and Lz? No, these operators don't commute. What about Px and Py? Can I have eigenfunction which is at the same time eigenfunction of Px and Py? Yes. Yeah. Can I have eigenfunction which is eigenfunction of x and y? Yeah, absolutely. Why not? What about Px and x? Can I have function which is eigenfunction of Px and x? What do you think? No. Yes? What about Px and y? Can I build a function which is going to be eigenfunction of Px and y?
Yes.
Yeah. So that's why I want to focus a little bit on this commutation relationship. So for me, it's very important then, because my angular momenta don't commute between themselves, I cannot build a state where Lx and Ly and Lz, they have certain value. In the same like here, I can build a state where my x and px will be certain. This is a basis for the uncertainty principle. Px and x don't commute. There is no way to build a state in which x and px are certain. And from Lx, Ly, and Lz, because they don't commute, I can pick only one of them. Let's say Lz. And I can make a state where Lz is certain. But Lx and Ly will be uncertain. I can build a state in which Lx is certain. But in this case, Ly and Lz will be uncertain. And the same goes for Ly. Because of this commutation relationship, I have certain restrictions, how many certain values or how many certain values I can have at the same time. But I'm lucky with L square, because L square commutes with everything. So then I can build a state which is, because they commute, that we can say that these operators share eigenfunctions. So I can build a state like this. It's called spherical harmonics. So if I apply my operator L square on this, I'm gonna get eigen value and the same function, and then one of these Lx or Ly or Lz. So usually people pick one of them and call this direction the quantization axis, some value. So why in this state we have certain L square and we have certain Lz, but we have uncertain Lx and we have uncertain Ly. So this function has certain Lz and L square, but we'll have uncertain Lx and Ly. And this is very important. So I'm gonna draw like a picture for you, and you should not look at this picture with full face into this picture. But this picture may explain something for you. So let's come back to this Cartesian x, y, and z. And let's say I have angular momentum as a vector. Can I draw this vector like this, for example? The answer is no, I cannot, because what's wrong with this? Because I'm gonna have very certain LZ, and I will have certain LX, and I will have certain LY, because my LX and LY will be zero. Would you agree with this? If this is the orientation of my vector L, then you know all three components. You know X is zero, which is certain value, yes? Y is zero, and you know that your Z component is the maximum possible. So this picture is not gonna work. So how can you build, how you can imagine the more quantum mechanical state? The quantum mechanical state, if you have certain Z component, you're not supposed to have certain X and Y components. So I'm going, let me tilt it a little bit. So this will be the length of the vector L, and I'm gonna have certain Z component, LZ, but I'm gonna rotate this vector around. So imagine that this vector L is not stationary. It's rotating, but this rotation not in time. This vector L is just spread it around z-axis. So basically this vector L forms a cone. So it goes all around. Does it have certain lengths? Yeah, absolutely, yeah. This length will be always the same. Does this state has certain LZ? Yeah, it's gonna have certain LZ all the time. Do you have a certain value of Lx? No, you don't have certain value of Lx. What about Ly? Do you have certain value for Ly? No. So this would be more quantum mechanical picture for angular momentum rather than this one. This is simply not possible in quantum mechanics. I don't know if I can just cross it like this. And the right side picture is okay. And this is we know from the very beginning, once we calculated the commutation relations. Yeah, commutation relations between different components of angular momentum. It's very interesting. When you apply operator L plus, remember we are talking about L plus. Operator L plus will supposed to rise LZ by H bar. Okay, so then when you want to increase operator LZ, the Z component, then you just move it up a little bit, and you have a cone with a smaller angle. So this cone will have a higher LZ. By H bar. But still, it will have the same shape. It will have certain LZ, certain L square, but it's not gonna have certain LX or LY. But I'm fine with this. There's no big problem. Can I build this Eigen Functions, eigenvalues? I can try to use techniques which we use for simple harmonic motion. So let's say you have a certain state, and then you have some constant C, and this constant C corresponds to eigenvalue of operator LZ. What if you apply operator L plus to this Y? this eigenvalue should increase, yeah? So then you can raise it to C plus H bar. I'm trying to make a reference to simple harmonic motion and rising and lowering operators. So then this would be the transition from one state to another state. What if you apply this twice? What if I consider L plus square applied to Y? What I'm gonna get?
C plus 2H bar.
Yeah, exactly. But I also can go down, yeah? If I try to apply L minus. And so if I apply this twice, I'm going to be C minus 2H bar. So you see there is a step, H bar. And then you can go by these steps. So it's if this is 0, then this is plus 1, this is plus 2, minus 1, minus 2. And you have and you can continue. When we were talking about simple harmonic motion, we say there is a limit for me. I can go lower than the ground state in terms of energy. In the theory of angular momentum, we also have limit. So apparently, if you can rotate this vector L in different directions, there will be maximum possible LZ, and there will be minimum possible LZ. So let's introduce them. LZ maximum. Traditionally, we just say H bar multiplied by some value L. And LZ minimum possible. H bar L, but negative. Apparently, I'm going to use the same value L, and I don't know this L. I'm going to find this L. So then L represents me the maximum possible angular momentum, and at the same time, it represents me the minimum possible value. Can I find this L? Well, I'm going to use the fact that the step between two allowed angular momenta is H bar. How many steps you have from minus L to plus L if your step is 1? How many steps? If I start from minimum possible, represented by minus L, and I will start to rise it by 1. So I can reach the maximum possible. How many steps? To L plus 1. And this number must be integer. Does it make sense, or is it complicated? Because you can step by 1, then the entire interval from minus L to L must be integer. It cannot be a half integer or some real number. You have integer number of steps, and each step is 1, plus 1, plus 2, plus 3. So then the total interval from minus L to L must be integer. We get restrictions from this for L. What kind of L I can have? Some integer number, minus 1, but integer number minus 1, it's also integer number. Yeah? Okay, I'm going to keep it, but apparently integer number minus 1, it's the same. integer number. So then my integer number over 2, this is the allowed values for the maximum and minimum angular momentum in terms of h bar. And then you can step between minimum and maximum only by h bar, by 1, in terms of this cell. Does it make sense? Even further, I can look at this integer with a little bit more attention. L equals integer number over 2. What if your integer number in numerator is even number? L would be integer. Yes? Because if this is an even number, you can divide it by 2, you're going to get integer values. But you have an options, and integer values could be 0, 1, 2, 3, and so on. What if you have odd number in the numerator? What kind of values for L I can have? Half integer. For example, 1/2, 3/2, 5/2, and so on. So from quantization of angular momentum, we can conclude that the LZ component and the maximum and minimum, at least at this point, can be only integer or half integer in terms of h bar. We don't have any other options for angular momentum, simply because of this L plus, L minus operator, because they can shift you by 1. And you have a minimum and maximum value, and from the symmetry, they should be defined by the same number L. So then you have 2L plus 1, it's a number of steps. And because every time you make a step by 1, the total number, the total interval must be an integer, and L itself can be either integer or half integer. It's very interesting. Then the wave function, let's talk about the angular momentum and spin, but spin probably we're going to talk about it later. So Eigen functions of LZ operator, let's find them. Eigen functions of LZ. I'm going to write it as minus I h bar d over d phi. Now I'm going to use coordinate representation for this LZ. I'm going to just solve this equation. LZ multiplied by function, I would like to have some constant c multiplied by the same function. But I suspect that my LZ should be between minus L and L. It should be either integer or half integer. I don't really expect any arbitrary values for this C. Okay, let's see what I'm gonna get. So if I apply this operator, I'm gonna get something like this. The derivatives from function y over angle phi, I should get the same function phi, or dy over d phi must be equal, let me see, I c over h bar y. Can I solve this equation? What would be my function? Of course, some integration constant multiplied by if you take derivatives, you get the same function, but this constant in front. Exponent, yeah.
Yeah,
I
C over H bar times
angle phi.
Yeah.
Very good. So now, I would like to recall that my functions, my value c, can be integer or half integer. What if I don't know this information? If I don't know this information, then my constant c can be anything. I don't have any restriction for this from this equation. Yeah, this would be solution of eigen problem for LZ for any eigenvalue. It could be even complex number. It could be positive. It could be negative. It could be integer, half integer, or real number, whatever. What kind of restrictions I actually have on this constant c? There is very non-trivial restriction which I want to introduce. What if you make a 360-degree rotation around the z-axis? What if you change angle phi to phi plus 2 pi? So what would it mean? So let's say you have one more time, x, y, z. So you have this point, which corresponds to a certain angle phi. What if you take phi and increase it by 2 pi? So instead of this point, you're gonna get the same point, yes? Rotation by 2 pi will bring you to the same point. So your wave function should not change if you come to the same point. Because it's the same point. You have only one value of your wave function at the same point. Wave function must be the same. So that means if you have this exponent I c phi over h bar, and then you change it to phi plus 2 pi, you would like to get the same value. Does it make sense? So the shift by 2 pi for this angle should not really do anything to your function. Then the extra multiplier on my left side, this one, must be equal to 1. No matter what. I don't want to have this 2 pi shift to change in any way the wave function. What I started with must be the same after the rotation. It will put a very strong restriction for this coefficient c. So when this exponent is equal to 1, exponent equal to 1 if you have integer number of 2 pi's. And so on. So then constant c must be integer number of h bar. So it can be where m is 0, 1, 2, and 3. So this is my eigenvalues of operator LZ. The allowed values for the component of angular momentum can be only integer number of h bar. It does coincide with this one, yeah? If my maximum and minimum are integer, then all numbers in between, if you make a step by one, all numbers for LZ will be integer numbers. And this is very good. These numbers I have to pick to describe angular motion of my quantum particle. Can I pick half integer numbers to describe angular momentum? Or better say orbital angular momentum. What about half integer? What will be your conclusion? Can I pick half integer values to describe orbital angular momentum? No, I'm not allowed. And then what we have achieved so far, we solve eigenvalue, eigenvectors problems for LZ. So we found that my eigenvalues for LZ can be only integer number from h bar. And also what we found as well, that this integer number must be confined between minus L and plus L, and the L corresponds to the maximum possible z component of my angular momentum. So then we have a very straightforward now consideration. So let's say if my L equals 0, then this number M can be 0 only. Because remember, M must be greater than minus L and less than plus L. So you go from minus L to plus L by step 1. This is called S state, when you don't have any angular momentum. What if your L is equal to 1? Well, your M can be minus 1, 0, and plus 1, based on the same rule. So then you have a vector of length 1. So you have a plus 1 state, 0, and minus 1. Plus 1 as a component LZ, 0, and minus 1. This is called P state. What if you have L equal to the maximum possible angular momentum? What will be allowed values for the Z component? So now your vector is longer. You have more different LZ. Minus 2, what's going to be next?
Minus 1.
Minus 1, and then
1,
0,
1, 2.
1 and 2. Okay, one more. L equal 3. M would be equal to,
Minus 3, minus 2.
yeah, like this. Exactly. The total number of states, 2L plus 1. So then the wave function for each of these, the wave function would be proportional exponent I, M, and phi. And M is one of them. M must be integer. And this is important because you are talking about orbital angular momentum. When you shift phi by 2 pi, you will arrive to the same point. And the wave function at the same point must have the same value. You can't have two values of the same function at the same point. That would be nonsense. what is interesting to notice at this point, that if you're talking about intrinsic angular momentum, so what is intrinsic angular momentum? We honestly don't know. But let's assume that if you have orbital angular momentum, so let's say you have a hoisting star and you have a planet, and planet is orbiting around, yeah? So you have orbital angular momentum. But you also have intrinsic angular momentum, S, or spin. So when you describe motion of particle around hoisting star, you introduce vector r, you introduce angle phi and all these coordinates, and when you make 2 pi rotation, you're coming to the same point. But for spin, I don't know if it's obvious to you or not. For spin, you don't have angle phi, it's intrinsic angular momentum. So for the spin, you don't have restriction like this. So for the spin, you have both possibilities. So because spin is not related to orbital motion, you don't have this condition when you shift angle phi by 2 pi. Then half integer values for spin they're allowed. So the spin can be integer. For example, photons, they have integer spin, and it can be half integer. But we're going to talk about spin maybe next time. So spin is different from all orbital angular momentum because you don't have this extra condition. To pi, yeah? What is the nature of this intrinsic angular momentum, which we call spin? It's not very clear. If you assume that your particle, they have an internal structure, like Earth, and Earth can spin, then you're probably fine with this. But some particles, like electron, they don't have internal structure. There is nothing to spin. And electron still has this intrinsic angular momentum. The spin of electron is 1/2. So then it's not easy to explain the nature of this intrinsic angular momentum. The only what I can say about it, that intrinsic angular momentum has no this restriction as orbital angular momentum. And when we are talking about motion of electron in a hydrogen atom, of course we are talking about this angular momentum, and then if you want to take into account electron spin, that would be next step for us, maybe for the next meeting. Okay, so at least we see a little bit more right now in terms of why you have only integer values for orbital angular momentum, and why for spin you have sometimes half integer values, like proton, neutron, electron, neutrinos, they all have the spin 1/2, half integer. The particles which are responsible for exchange for the interaction, like photons or bosons, like W bosons, they have integer spin. Spin equal 1, basically. And what about operator L square? So this was Eigen function of operator LZ. We can share, we can have the same functions and make them Eigen functions of operator L square. Actually, I can build some of them And then I probably can just write for you what is operator L square would be. It would be something like minus h bar square. Let me think about it. There should be angular part of the Laplacian. 1 over sine theta d theta sine theta d theta plus 1 over sine square theta d phi square. So in spherical coordinates, this operator looks a little bit nasty. You can try to formulate a problem for eigenvalues and eigenproblems, and there are ways how you can solve this in the most elegant ways. I can probably tell you that let's say you have a function y which corresponds to maximum value, like you have a lambda and m equal L. If you apply operator L plus, because you already have maximum component, then you should get 0. So from this, you can find y lambda L. And from this, you can find the solution of this. So I believe the solution would be sine angle theta power L exponent I, L, and phi. So then that would be solution of this equation, the proportionality here. So if you apply now operator L square to this function, you can get the value for the lambda. So the lambda is the following. Lambda y m lambda. Lambda, the meaning of lambda would be the value for the magnitude of the angular momentum. So ns would be equal to L multiplied by L plus 1, and of course h bar square. H bar square multiplied by L plus 1. So the magnitude of angular momentum can be related to the maximum LZ component. And you can notice that the magnitude is slightly longer than L square. And this is also can be explained by this nice picture. If you have maximum component L, it's a maximum Z component, yeah? So then the length of this vector should be longer a little bit than the maximum Z component. So that's why your lambda is not L square. It's L plus 1. And again, this L plus 1 is not easy to prove. You just have to kind of do the calculations. And the theory of angular momentum is not very simple as well. So then the summary of this. So we can formulate problem and we can try to find the eigenvalues and eigenfunctions of operator which represent me the angular momentum square. So this is eigenfunction, this is eigenvalue. So the L here, and I'm sorry, I always forget to put h bar square. Yeah? It's just a habit. So this value L can be 0 or 1 or 2 or 3. So I'm not allowed to have half integer values for angular momentum if I speak about orbital motion. And at the same time, the same function would be Eigen function of operator LZ. I can share these wave functions because they commute. So my M would be from minus L to plus L. So this YLM they call spherical harmonics. So people know them. I can list maybe 1, 2, 3. It's not a big deal. For me, it will be more important that they are Eigen functions of operator LZ, so you know what is the value for LZ in each state, and the value is given by M. It's kind of magnetic quantum number. And this M is confined between minimum and maximum value. And also, this same state will have certain L square. So basically, the magnitude of the angular momentum, which also can be related to this maximum Z component as L plus 1. So maybe some of them, for example, Y0, 0, L equals 0, M equals 0. It's proportional to constant. It's basically 1 over square root of 4 pi. It's called S state, spherical state. So there is no angular momentum in this state. L equals 0. Y1 plus 1. As I promised you, when you have a maximum M, you should have sign in this power. Sorry. That is proportional to sine theta exponent I phi. And of course, you have to put some normalization constant here. Then you can apply lowering operator to this state. 1, 0. You're going to have a cos theta, and there is no exponent because I am phi, your M number, quantum number is 0. So then you don't have it. And you have a Y1 minus 1. And this is the lowest possible state in terms of angular momentum. So then it could be sine theta exponent minus I phi. So this is constant. And these functions, they depend on angle theta and phi. So this is called P state. L equal 1. And then you can build L equal 2, yeah? 2 plus 2, which probably you can guess what will be spherical harmonic for L equal 2, so-called D state. It should be sine square theta exponent, because my projection is plus 2, so I put plus 2 I phi, yeah? But you have 5 different components in this D state. You can apply lowering operator and get all the other states from this 2 plus 2. Let's talk about P state, because S state is trivial. S state means that there is no dependence on angle. You have a spherical distribution in terms of angles. But P state would be interesting, because if I make it absolute value square, then I'm gonna get sine square or cos square. Sine square when you have a maximum possible component. So sine square theta. Then the sine is maximum when angle is pi over 2 or minus pi over 2. And sine is 0 when angle is 0. So I'm talking about angle theta. So I'm going to have a state something like this. And it would be the same for m equal plus 1 and minus 1, because when you take absolute value square, this phase will go away. So I'm going to have the sine square. So this would be p-state wave function for m equal plus 1 or minus 1. The only difference probably will be rotation. It's going to rotate in one direction for m equal plus 1, and it can rotate in opposite direction for m equal minus 1. So is it true? It seems so, yeah? Or not? The maximum would be when my... No, this is not true. Wait a second. Angle theta is calculated relative to z. Oh, this is m equals 0, sorry. This is cos. This is not sine. Because my fault, I'm sorry. I just missed. Angle theta is calculated from z direction. So angle theta equals 0 means here. So this is where sine would be 0. So this is cos, of course. So this is m equals 0 state. So in this rotation, your z component is of angular momentum is 0. And you have another one when you actually have plus minus. Yeah, now I see my mistake. So sine square will be maximum when angle equal pi over 2, but pi over 2 relative to z. So then it's going to be like this. And then you rotate it. You can imagine this rotation. So you have such kind of shape which you rotate around z axis. And you can rotate it in one direction, that would be m equal plus 1, or you can rotate it in opposite direction, that would be m equal minus 1. So it's like some flat object. And this object is in xy plane, which you can rotate one direction or opposite direction. So this will give you density or probability of distribution of your particle in over the angles. So then if you look at other states, like T state and further, then your distribution in space will be more and more complicated. Basically, that's it. And this is a very brief introduction to orbital angular momentum. Do you have questions? No, I guess it's too much, yeah? Okay. I'm gonna use this in very, very little for hydrogen, because for hydrogen we have to solve 3D problem, and we're gonna do this in spherical coordinates. And for angular part, we're gonna use the knowledge we already have. Now, what else should I say about angular momentum before I move on? Maybe that's it. Yeah, spherical functions, the eigenvalues. Basically, this is called quantization of angular momentum and orbital angular momentum. We are not talking about spin. Probably we cannot finish today hydrogen because hydrogen requires consideration. But we can start talking about hydrogen atom. We can move to second part. So we're gonna solve stationary Schrödinger equation for 3D, yeah, for hydrogen. So you have a central part, heavy nucleus, which has some charge. And for this charge, you can just put some Z elementary charge, and you have an electron moving around, and you have distance r. So the electron can feel potential created by positively charged nucleus. So this potential energy must enter the Hamiltonian. And then what can be allowed energies and what can be allowed distribution of the electron around this nucleus, which has certain energy. So we ask to solve for eigenvalues and Eigen Functions, solving the Schrödinger equation. We already have experience, yes, we have experience with infinite square well potential, finite square well potential, and we have experience with simple harmonic motion. But those problems, they were one-dimensional. So for three-dimensional motion, my Hamiltonian would be kinetic energy, which is P as a vector square over 2m. So this P square is a magnitude of three-dimensional vector, plus potential energy. Potential energy of interaction between the electron and the nucleus. So this energy of interaction we can borrow from electrostatic, and then what we discussed in physics too. So we can say P as the operator square over 2m. The energy of interaction between two charges can be written like this. I don't know, some of you probably remember this, especially if you took or just taken physics 2. Now, I'm gonna plug charges how they are. One charge is Z, elementary charge. The charge of electron is negative E. So I'm gonna put negative sign. And the constant K. Finally, it will be convenient for me to just label all this combination with one symbol. Let's call this beta. So this would be my potential, which I'm gonna draw in a minute. So the beta will characterize me the strength of the interaction. Of this Coulomb attraction between the electron and the nucleus. This is a 1. So I kind of understand what is the potential energy of interaction between the electron and the nucleus. And Z, if you don't know, Z just characterize how many protons inside the nucleus, so it's atomic number. So depending on what kind of elements you're talking, atomic number, and constant k equals 1 over 4 pi epsilon naught is just a fundamental constant, roughly 9, 10 to the power 9 in some units, Newton, meter square, Coulomb square, something like this. And E is the elementary charge. What is more interesting, it's a momentum. Momentum equals to minus I h bar d over dx. But that was in 1D. So now we can say this is x component only. So what we have in kinetic energy, we have p square. This means px square plus py square plus pz square. So this means you have something like this, minus I h bar dx square plus minus I h bar dy square. So the y component and minus I h bar dz square. Okay, so then I have to work on this a little bit more to finally write down the equation of motion. So my p square would be equal to minus h bar square dx square plus dy square plus dz square. So this operator has a name. When you have this first derivative square in all directions and you sum up them, how do you call this operator? They use a symbol like a triangle for this. It's called Laplacian. So Laplacian in Cartesian coordinates is second derivatives over x, but then when you apply this operator twice, it's going to be second derivatives, yeah? Plus second derivatives over y plus second derivatives over z. What about spherical coordinates? Well, spherical coordinates, it's more complicated, yeah? It's something like this. 1 over, let me write it like this. D over dr, second derivatives, plus 2 over r, d over dr. So this is the radial part of the Laplacian. And you have angular part. So the angular part will have 1 over r squared multiplier, and then something like this. And lucky for us, we already have seen this. Plus 1 over sine square d phi square. So it's very convenient to split your Laplacian into radial part plus 1 over r squared multiplied by angular part. So this omega represent me a solid angle. So all these brackets would be angular part of my Laplacian. And we have to plug this operator to my wavefund, to my Hamiltonian. And we have to solve the problem for eigenvalues and eigenvectors. So you see, it is not a simple and trivial problem. But there is something very good about it. I don't know if you noticed this or not. The angular part of the Laplacian, does it remind you something? Because I already wrote it today. I'm afraid I will have to go too far. No, not too far. Look at this. This is exactly operator angular momentum square. It's not a coincidence, of course, but we are very lucky that this complicated angular part of the Laplacian can be expressed as our angular momentum square operator. And then if I pick my functions, Eigen functions of L square, I can replace the action of this operator with eigenvalue. This will be tremendous simplification of the problem. So I have radial part again. And then I have angular part, which is minus L square over h bar square multiplied over r square. For now, it's just a very convenient way to write it down, the Laplacian for me. But later, when I pick my function as eigenfunction of L square later, I can replace it with something more simple, like this. So the L square, I'm going to change h bar square L plus 1. And suddenly, I have one-dimensional problem again, because I have to solve Schrödinger equation only for the radial motion, because all this complication with this angular part of the Laplacian will reduce to just a fixed value of angular momentum. So this transition, it's very beautiful. It helps me to save a lot of time. I'm gonna justify it to you right now, and then I'm gonna prepare to solve this Schrödinger equation, but we're gonna finish next time. Of course, we don't have time today. Unfortunately, I underestimate this angular momentum part. It took too much time. So now, let me still keep L square as the angular part of the Laplacian. And let me write Schrödinger equation for you. I'm going to come back to the Schrödinger equation, to p square, and to my potential energy. So h psi equal e psi. Now I'm going to change minus h bar square 2m Laplacian so this is a kinetic energy, the operator p square, and potential energy. So then I'm gonna have minus h bar square 2m radial part. Angular part, this one. acting on my wave function. These are operators. This is a very complicated operator. Basically, it has all these derivatives over angles, and it has radial part. Then I have potential energy, which is 1 over r. And then it must be equal some eigenvalue and the wave function. So then I would say it's relatively simple to show that your L square is commuting with this Hamiltonian. So then basically it means that your system has spherical symmetry. If you rotate your hydrogen atom, you're not gonna change energy of your Hamiltonian. So we have spherical symmetry. From this spherical symmetry, we can say that H and L square and LZ and any L, actually it could be a more strong statement. We can put some any component of angular momentum. They share Eigen functions. Because they commute. And commute, because remember LZ was rotation about z direction. If you take your original Hamiltonian, if you rotate it about z direction, just try to rotate it about z direction. Are you going to change potential energy? No. Your potential energy depends on the distance. Distance is not going to change if you rotate it. Are you going to change p square if you rotate it around it? No, you're not going to change it. So the fact that Hamiltonian commute with L, any component of L, that's because your system has spherical symmetry. And that's why we can have common Eigen functions that can have certain energy, certain LZ, and certain L square at the same time. So psi has certain energy, LZ, and L square. This means also that it's going to be Eigen function of L square and LZ. That means that psi must be proportional y Lm, which is function of angles. Because I spent more than 1 hour to solve this problem for LZ and L square. So then the angular part, I don't want to worry about angular part anymore. I would like to say that my psi satisfies this equation. And on top of this, it should satisfy the Schrödinger equation. I can do this because they commute. And they commute because of the spherical symmetry. So then one way to present my solution would be to say, okay, if I have my wave function, then the angular part would be given by spherical harmonics. And the radial part, the distribution along the radius would be given some another function. So I separate the variables. I have a distribution along radius, and angular part I know because of these two equations. This one and this one. I already know solution of them. These are spherical functions. What I don't know is my radial distribution and how electrons are distributed along radius. Well, this would be the subject for the next class. How you can find the radial distribution, and then you can find the energy, the spectrum of hydrogen atoms. Okay, so can I plug this wave function in this form into this equation? Yes, I can, but I will have L square acting on my wave function. I know I have a radial part, of course, but I also have angular part, and this L square will be applied to this side. But when L square is applied to wave function, I'm going to get L and L plus 1 because I know it's a spherical function. I know its eigenvalue, eigenfunction of L square. So that's why I can basically replace L square with L and L plus 1 inside the Schrödinger equation. So I'm going to rewrite this equation right now with specific form of my wave function. So something like this. Minus h bar square over 2m, the radial part of the Laplacian. Then because I'm going to apply this to R and Y Lm, I can work a little bit with this angular part. I'm going to replace it with negative L plus 1 over R squared minus beta over R radial wave function, angular wave function. So this part does not change. And of course I have this energy. What I can do now is cancel angular part. But I have knowledge about angular part from this L plus 1 term. Because the operator L square acted on my wave function, and you extract some knowledge about angular momentum from the wave function. So I still have memory about what kind of wave function it was. Okay, usually people do open brackets. You have a radial part, you have energy part, and this middle term corresponds to what's called centrifugal potential energy. You can combine this together with the Coulomb interaction. So then you have something like this. The radial part of your Schrödinger equation. So the prime corresponds to derivatives over R. So it's the second derivatives, this is first derivatives from this R. Then I'm gonna open brackets and I have this h bar square 2m. So I'm gonna have plus. I don't have brackets here, just L plus 1 over 2m R square, this term, minus beta over R combination of potential energy and centrifugal term equals to energy multiplied by R. So in this equation, I don't know what is energy, and of course I don't know what is function R. I have knowledge about the interaction. So this is the potential energy of interaction between electron and the nucleus, beta. And I also have knowledge about the angular momentum of my particle. And angular momentum is conserved, so that's why I could do this. So next time we can solve this equation. The solution of this equation will give you the spectrum which I would like to have for hydrogen-like atoms. Now, if you let me to have a couple more minutes, I'm going to talk a little bit about this it's called effective potential. So this effective potential is not something new or something people don't know in quantum mechanics. So it's called effective potential. It's L square over 2mr square minus beta over r. So it's effective potential for radial motion. And this is classical expression. When you move from classical to quantum, you have to replace your L square with just h bar square L plus 1. But even in classical physics, we have the same effective potential. So if I try to draw the graph of this effective potential as a function of r, you would probably see that at very small r, this centrifugal potential will be very large and positive. At very large r, it's going to be very small, so you have only interaction. So this asymptotic behavior is minus beta over r, and this asymptotic behavior is 1 over r squared. So then if you combine them, this is your potential, effective potential for radial motion.
Just to detail, is beta over r in the formula.
Say it again?
There's beta over r, not r squared in the formula. It's just a detail.
Oh yeah, absolutely, yeah. Yeah, my mistake, sorry. Of course, beta over r. So now if you have a certain energy of your particle, like electron, if you're talking about nucleus and electron, or it could be central body and a planet. Because central body and a planet, they have the same type of interaction, just the constant is going to be different. So if you have certain energy, then the particle is going to move between these two turning points. One point will be closest approach. In planetary physics, you would call this perigee. Yeah? And the other point would be the furthest separation. It's apogee. So it's going to be an ellipse. You have a center, you have perigee, and you have apogee. So if you treat your electron as a classical particle, then you have to solve this problem and you will get an ellipse as a solution. So you will have a perigee, you have an apogee, your angular momentum is conserved, that will give you the second Kepler law, and this is a very well-known problem in classical physics, and of course it's solved. So when you try to pick different energies, you can get different motion. So sometimes your energy is minimum. In this case, you don't have radial motion. You have your only one allowed radius, this would be circular motion. What is interesting about this centrifugal potential, it does not let you to come very close to the center. This is the center. The centrifugal potential grows as a 1 over r square. It does not let you to find, to approach the center. You have to have a very high energy, and it's going to be not bound state anymore if you want to come closer and closer to the center. Or you can have L equals 0. If you have L equals 0, then of course it will be different potential. Yeah? So L equals 0, this one. But L equals 0 means you have no angular momentum. You have a central body, you have either an electron or a planet, and your motion is along radius. So of course you're going to fall to the center because you don't have angular momentum. But if you give some angular momentum, you can never reach the center because this centrifugal potential basically repel you from approaching this. And it's very nice that in quantum mechanics, we have absolutely the same centrifugal potential. The only what we have to do, we have to quantize angular momentum. We have to replace this L square with h bar square L multiplied by L plus 1, where L plays role the maximum LZ component on this. I'm sure you have seen this diagram, this graph, if you ever try to solve Kepler problem. Basically, what we're trying to solve right now is also a Kepler problem. But we're going to apply this to hydrogen-like atoms when you have one electron orbiting around a nucleus. So you see, even to reach this point, it took more than 2 hours for me. So this is very, and I use symmetry. I use a lot of symmetry because the angular part of the problem I got for free. Okay, thank you so much.
Thank you very much.